In this module, we are going to complete the discussion on the pool boiling curve. And to just get started, this is the schematic of the pool boiling curve that one would come across in most textbooks. And last time, in the last module, when we talked about the pool boiling curve, we said that initially if we talk of a pool where water, for example, at atmospheric pressure is being heated, you would start with, say for example, I would take a pool here and have water, and I have a control for wall heat flux, and for example I take measure time here, heat flux here, and the wall temperature at this location T wall, let me call it, and there could be a T bulk mean in the pool, which could be just like your mixing cup temperature. So, this is some T1, T2, T3, so on and so forth. And if I make a very nice record of what is happening, what you will see is that this would be some Q double prime 1 value, this would be some TW1, and the convection currents would be set up. The convection currents would become more active and stronger, and this the bulk mean temperature will progressively increase with time. This is all normal commonsensical stuff. T wall also will increase with time, and heat flux you are progressively controlling and increasing. So, what you would see is that the natural convection aspect becomes a little bit more predominant, more active, and if I plot this Q double prime versus T wall minus T sat, this is a log scale. So, you would have 1, 2, 3, 4 some points like this, and mind you, natural convection heat transfer, the Q double prime by delta T is a measure of the heat transfer coefficient. So, the slope of this boiling curve at any location is a representation of the heat transfer coefficient. So, low heat transfer coefficient, the slope is going to be very, very small. You would see something which is like this, a line which is almost parallel to the x axis, slightly inclined by a few degrees, and this is what is the natural convection region. And you have your single phase heat transfer correlations that have been developed, which you can use to predict the heat transfer coefficient in this part. Okay. Now, the activity for boiling is going to start. When the wall temperature, remember we are talking about water which is at atmospheric pressure, the saturation temperature is 100 degrees centigrade, and please remember that in our basic thermodynamics, when we had basic thermodynamics, this is one of your earlier modules, we said if the pressure is held constant and I progressively increase the temperature, and let us do this for water at 1 atmospheric pressure, when the temperature reaches 100 degrees centigrade, you would start changing the phase from single phase liquid to single phase vapor. This is what we have been told, and this is correct. There is nothing wrong with that, except that it does not happen exactly at 100 degrees centigrade, because the bulk fluid, I hope all of you are able to appreciate that in your single phase heat transfer, we had this concept of temperature gradient, and the temperature gradient is nothing but how temperature varies in the fluid from the wall. So, if this is the wall and this is the, if I were to plot a temperature variation, always the wall is going to be the highest temperature, and the temperature is going to progressively decrease as I move in the fluid, right. So, if I get the gradient is nothing but dt by dy at this wall. This is at a given time t. At a slightly higher time, next time I would have a slope which is probably slightly higher, the green dashed line. At some other time I might have a slope which is slightly larger, the green thick line. point I am trying to say is the wall temperature also increases, T wall increases with time, T bulk mean increases with time, Q double prime increases with time, though we are going to keep it constant for a given set of time. So, there is a situation where the bulk fluid is at a temperature. What is bulk mean temperature? I am not sure if you remember. Bulk mean temperature, if you do an energy balance, MCPT bulk mean is nothing but an integrated value. So, this is temperature at every location. You take it, and the mixing cup temperature was defined. I hope you remember this. The mixing cup temperature or bulk mean temperature for flow, bulk mean temperature was defined this way: m dot Cp T bulk mean is equal to rho u of r Cp T of r comma z dA integrated over the area. And from this you would write this as rho u bulk mean A cross section Cp T bulk mean is equal to this integral, and from this you get your bulk mean temperature. Fundamentally, bulk mean temperature is nothing but an average value of the temperature that the fluid would have. So, this fluid is going to have some bulk mean temperature, which is nothing but a average value of this temperature distribution. Is that right? So, I am going to have a temperature which is higher than the bulk mean temperature near the wall. So, if I plot this temperature profile like this, and this is done primarily to show things in right perspective, I am exaggerating the slope, and this green dash line is, let us say, your bulk mean temperature. This is your T wall, this is your T, and T bulk mean is here. So, what do I see? I see a line which corresponds to T is equal to T bulk mean, and this portion of the fluid is going to be at a temperature greater than T bulk mean. This portion of the fluid is at a temperature lower than T bulk mean, right. So, the T wall is going to be greater than T bulk mean. Is that a fair statement? You can see this is going to be T bulk, T wall, T bulk mean is here. So, when I say boiling or change of phase happens at T sat, when T wall equal to T sat, what can, based on this analogy, this logic, what can we say about the bulk mean temperature? T bulk mean temperature is lower than T sat. Is that a correct statement? This number is T sat, let us say 100 degree, then only the layer of fluid in contact with the wall would be at 100 degree because of no thermal slip condition. The first layer, imagine this water to be like a sheet of paper, several sheets of paper stacked. The first layer is going to be at the temperature of the wall. If wall is equal to T sat, which is 100 degrees centigrade, I am going to say that the bulk fluid temperature is definitely going to be lower than T sat, which is 100. So, when the first layer of the fluid is at 100 degrees centigrade, boiling does not happen. Okay, that is the first thing we need to understand. Boiling will happen when I have a wall temperature T wall greater than T sat. T bulk mean may be less than T sat or equal to T sat. I do not know, because if this wall temperature becomes 110, obviously T bulk mean could be saturation temperature. All I am interested is in this inequality. When T wall becomes greater than T sat, I have to start being concerned about whether boiling is going to happen or no. For a given surface fluid combination, by that I mean I have a stainless steel tube, I have a copper tube, I have water, I have stainless steel tube with surface which is made rough, copper tube which has some surface coatings which are done for enhancement of heat transfer. Depending on the surface fluid combination, the nature of the surface finish and the fluid which is in contact with the surface, the aspect of boiling is going to be greatly different. Why is it different? Because boiling happens at microscopic level. If you see, boiling happens because of the process of nucleation in cavities. Nucleation, by that I mean it's a formation of bubble. Now please go back and reflect at boiling of water for tea. When you had this surface, if I am going to have a vessel, and you would see very clearly, this is the top view, if the gas is kept at a low flame, you would see one small bubble coming out from this point. That bubble would be there on the surface, then it will leave the surface, come out to somewhere here and then collapse. After some time, you don't change the flame, the bubble will come out from the same spot, move up to the top and then collapse. Simultaneously, another point B, a bubble would be generated, that would come, do the same thing. Later on at time T3, this is a point C where bubble would be formed. This process of bubble being formed at specific sites, all of us have observed this, at specific sites at specific different times is a result of the fact that boiling is a very local phenomena and it is governed by the process of bubble nucleation, meaning this is the birth of the bubble. Nucleation means this process where the bubble is formed inside on the surface of the heating surface. You have certain pits and cavities of various shapes and sizes where there could be entrapped air, etc. The bubble would be formed at that surface. Not all cavities would support nucleation, we are not going into the details of it. When the size of the bubble becomes sufficient such that it can come out of the cavity, that is why you don't have the bubbles coming out at the same time. So when the force balance between the inertial force, pressure and the surface tension forces is such that the buoyancy force is such that the bubble can leave the surface, the bubble comes out. When the bubble comes out, it encounters various layers of fluid at slightly different temperatures, progressively decreasing. The bubble came out from a surface which had to be greater than Tsat. It will encounter a layer of fluid which is equal to Tsat somewhere here, somewhere in this path. Okay, let us say Tsat was here, for example. Okay, and this is all greater than Tsat. T bulk mean is somewhere in the middle. The bubble will rise up to this point, and when the sheet of Tsat, the plane where Tsat is, comes in contact with the bubble, it is still hot enough. When the bubble crosses this sheet, it encounters colder fluid, and therefore the bubble which is having higher energy would give away the energy to the colder fluid and collapse. Okay, that is why the bubble which started off when you are boiling tea came up to a certain level and then vanished. After some time, bubble from the same location, if you observe, would rise to a slightly higher location in the pool and then collapse. Afterwards, the bubble will rise up to the free surface and not collapse at all. That is because the bulk fluid is slowly getting heated up, and as the bulk fluid gets heated up, the location or the locus of saturation temperature keeps going up in the pool, and therefore eventually the pool is completely going to be saturated. Where does all this lead us to? The point I wanted to make was that boiling doesn't happen at one shot. It is a continuous process which happens when the first nucleation starts when wall temperature is greater than Tsat. How much greater? We don't know. It depends on the surface and fluid combination. It depends on the pressure. It depends on various aspects. It's a very complex phenomena. But T wall equal to Tsat, T wall equal to Tsat, there will be no nucleation or boiling. T wall greater than Tsat by certain amount, that certain amount is called the wall superheat. T wall minus Tsat is the wall superheat that is required for nucleation, that is specific, and this is obtained from empirical correlation. This is from empirical correlation. This is a function of surface conditions, fluid properties, etc. Various things. So, when T wall minus T sat I am trying to plot, this should be greater than a critical value T wall minus T sat greater than delta T critical for nucleation. Once this is achieved, that means once wall temperature, say for example this comes to be 2.3 degrees centigrade, that means for this fluid surface combination, when T wall equal to 102.3 degrees centigrade, then nucleation would first begin. By that I mean a bubble which is formed would be able to come out of the surface and you would be able to have the process of boiling started from a particular cavity at least. Now, depending on the cavity size, the nature of the amount of superheat required for that particular cavity is going to be different. We are not getting into the details. The boiling curve, or the moment you have this nucleation which is going to start, you would start to see a small deviation or a slight increase in the heat transfer. Why? Because from here on, slight increase in the heat transfer will be seen because the latent heat starts to get used by the fluid, and as the wall temperature progressively increases, wall temperature was 100, nothing happened, slightly more than 100, one cavity came up, therefore it took away a certain amount of latent heat. Slightly more than the previous value, one other cavity started to become active and the first cavity bubble could leave the surface, therefore the latent heat went away along with it. So, the process of boiling has started even when the natural convection is going on simultaneously, and you start to see an increase in the heat transfer coefficient like this. Finally, there is a stage when the entire surface starts to be active in terms of boiling, and this asymptotic joining of the natural convection and the nucleate boiling curve, this is what you see in textbooks. You see this, okay. This part onwards is the nucleate boiling, okay. Nucleate boiling, textbooks divide this into partial nucleate boiling and fully developed nucleate boiling. We are not going into the great details of it. Partial is where few cavities are active, the cavities which are active, the bubble comes out of the surface and can collapse. Certain cavities will be such that the bubble goes fully up to the free surface. When all the cavities become active, when the wall temperature is such that all the cavities that are there on the surface are becoming active, you would call this as fully developed nucleate boiling. And this process continues for a reasonable amount of time. By that I mean, nucleate boiling is going to be the best form of heat transfer for us. The slope of this is typically what you would see is Q double prime is proportional to delta T sat, typically to the power 3 to 5. 3 to 5, it is not 3.5, 3 to 5. So, the slope would be either 3 or 4 or 5, 4.25, etc. So, different surface fluid combination you would have different slopes, but the broad nature of the curve is going to be the same. As I continue to heat, as I continue to supply heat, somewhere when this is something which you can again do as a thought experiment at home, you have started boiling for tea and then suddenly increase the gas to high flame, you would see a sudden burst of bubbles, you would see a violent thing happening at the surface. This process where you would, it's very hard to do it at home and get through this thing of CHF. All of you would have seen at some point of time eaten dosa at a roadside dhaba. So, you would have seen the guy, the dosa person, if this is the pan, he would sprinkle cold water onto this surface. And those of you who have attempted making of dosa at home, you realize that when this pan is very hot, for you to be able to spread the batter onto the pan is very, very difficult. Okay, but when the pan is at right temperature, you will be able to coat the pan completely with the dosa batter. What is different? The pan is the same, the batter is the same, but in one case you are unable to spread the batter nicely, in other case you are able to do it. It depends on the temperature of the heated surface. The pan, when it is very, very hot, what happens is the batter, let us say instead of batter, let us say droplets, the water which I sprinkle, the person sprinkles water on the pan, the liquid is not able to come in contact with the heated surface, it will just bounce from the surface. And what will happen is this droplet would stay above the surface, because the moment the liquid comes in contact with the heated surface, vapor gets generated because of this very high temperature, and this vapor will form a cushion between the heated surface and the liquid droplets, and therefore you would see these droplets dancing all over the surface. I am sure all of us have seen this, may not have noticed it with that much of intent, but when you try making dosa next time, if your batter doesn't spread, it is because of this, because the moisture in the batter, the water evaporates and forms a cushion of vapor which prevents us from spreading the batter. If I reduce the wall temperature, that is why he splashes water on it, and once he splashes, the wall temperature reduces, he uses a cloth to clean up so that the temperature is kind of made uniform, and then he pours the batter. This very, very fundamental aspect is so important in boiling, is that the lack of contact between the liquid and the heated surface is very, very bad. That point where the liquid loses contact with the heated surface, because T wall becomes much greater than where liquid can establish contact, is very, very dangerous from heat exchange point of view, from engineering point of view. That point where the contact is lost should never be achieved, because what will happen is, when the if I have a tube and water is flowing through this, suppose there is a local hot spot. Local hot spot means where there is some kind of flow maldistribution, and you come up to a surface where there is no flow in this path, and you are supplying heat. There is no sink for the heat, and this wall temperature here, T wall, will start to rise significantly, and because T wall starts to rise, you would lose the structural integrity of the surface. Why we are going to go to that is, when the boiling continues, and this experiment that we did in a pool, suppose the pool is open, you're starting to boil water for tea and you allow it to keep on evaporating, what happens to the surface? Eventually the surface starts to become visible without the water, and if you are supplying heat further, the wall temperature will start to increase. So when no water is there in the vessel, the wall temperature will start to increase rapidly, and that increase is what you would see here. Even for a small change in the heat flux, the wall temperature will rise appreciably. This may not be so clear in this pool experiment. However, if I take the same problem and I use a electric heating, a wire through which current is supplied, now, and this is the pool here, okay, when the wall temperature is such that, now let us go back to the tawa case, where this is the wire and there is a pool of vapor which is formed. This is a cushion of vapor and liquid is still there here. This is the cushion of vapor which is formed on the surface. What will happen? I am supplying heat more and more, and this is the heater wire. Liquid is still there, but because the bubble generation is so rapid, bubble generation is so high, rate very high, and that is not compensated. So I have so many bubbles coming out from the surface at a very fast rate, because before one bubble leaves another is ready, and because the system has attained steady state, now I increase the heat further, more and more bubbles are generated. There is no time for fresh liquid to come, and even if fresh liquid is able to come to the surface, the liquid itself is hot enough. So T bulk mean is also high, equal to T sat. So you don't need any extra time for the liquid to become vapor, and therefore the sustaining this nucleation is almost it just keeps going on autopilot mode. And because bubbles get generated so rapidly and fresh liquid is not able to come and take away more heat, this forms like a insulating blanket. This insulating blanket is what you see in in case of the tawa also, the steam vapor forms a cushion, and that cushion prevents further contact of liquid with the heated surface, and because of that you see the wall temperature rising. When I supply heat, Q double prime is T wall minus T sat into some quantity, is proportional to T wall minus T sat. If Q double prime is increasing and T sat is virtually constant, what is going to happen? TW has to increase, and that is exactly what is happening here. And this point where the first time this excursion or rapid increase in the wall temperature happens, that point is given various names. This is called as the point of critical heat flux, or I will use what is told typically, this is called the point of burnout or dry out. All these are used repeatedly interchangeably. I will tell you in the next module what is the correct representation for this point. When the excursion in the wall temperature happens for the first time, this is this change in slope. For a small change in heat flux, you will see a very large change in the wall temperature, and you continue to increase the heat flux, you go into what is called as film boiling, where there is no more liquid contact with the heated surface, you have only vapor and you have liquid on top, and this liquid is unable to come in contact with the heated surface, and you have vapor which is dominating resistance to heat transfer. Remember, thermal conductivity of vapor is very small, so the wall temperature further increases rapidly. Remember, this is a log plot. So this delta T that you are talking about, which is like 5 degrees here, is now of the order of 700 or 800 degrees and further increases rapidly. This is called as film boiling. So when I increase the heat flux, I go from nucleate boiling, natural convection to nucleate boiling, point of CHF, and then to film boiling. In the next module, we will try to cover wall temperature controlled case. This was a wall heat flux controlled case. We will look at the wall temperature controlled case. Thank you.